Hey guys, welcome to the Paris segment of the Global Video Tech Meetup. We have an hour of talks for you tonight. We'll be starting off with Phil Harrison and Raphaël Goldwaser from AWS telling the story of channel assembly. And then we're going to have Daniel Hoelbling-Inzko from Bitmovin, who will be talking about why time series databases are a bad fit for video analytics time series data. Just a quick shout out before that to our annual sponsors this year, Broadpeak and Lumen. Thank you so much for supporting and helping us finance our activities. Hopefully we'll be able to use some of that towards some actual in-person events later this year. We obviously can't wait to see everyone again. So with that, I will hand it off to Phil and Raphaël.
Hi everyone, my name is Phil Harrison and I am the product manager for AWS Elemeental MediaTailor's new feature called Channel Assembly.
Hello everyone, my name is Raphaël Goldwaser and I'm a specialist solution architect in the media industry for AWS. So Phil, we saw that last year in the news that even Netflix has launched an experiment in France named Direct to create a live linear channel with a mix of French content and international film. So tell me more about channel assembly. How did you get to create such a system? Is that something you hear from customers to relinearize their content?
Yeah, it's a mouthful of a word, isn't it? It took me about 6 months to learn the word, and I still struggle to say it. Relinearization. Funnily enough, the idea of this type of thing actually came to me quite some time ago. I was watching an episode of Rick and Morty, and in one of the episodes, they have access to a cable set-top box that has access to all the channels of the multiverse. And so there's like millions upon millions of different types of channels, and they can just sit back and watch literally whatever they want. And it has some really weird and wonderful stuff. And so that got me thinking is like, we're living in a world now where so much consumption of linear TV is moving to online. Why are we still operating with the same paradigm of, say, broadcast channels that are simply replicated online? Why haven't we moved past that and created many streaming only channels with personalization and kind of high quality and all of the things that I suppose Netflix are known for as well? And then that sort of genesis of an idea is something that happens quite a lot within AWS, where you're encouraged to go and unpick that thread and work out exactly if there's something in it. And although the concept of sort of channel assembly wasn't a very, I would say, unique idea, the part that is unique is the way in which we're doing it by doing purely manifest manipulation. And I'll talk a little bit about that in a moment. But I think what I wanted to first do was talk a little bit about the challenges of creating a linear TV channel for online only streaming. What happens usually is you need to go and interface with the traditional broadcasting side of the business, so the broadcast operations that run playout servers and other systems that are used for, say, DVB-T, DVB-C, DVB-S style transmission, and that can be incredibly complex. And I'm sure you'll put a slide on screen to show just how many components can be involved in that transmission chain. And a lot of that complexity on the technical side, on the cost side, on the infrastructure side is redundant because it's there to serve the purpose of traditional broadcast, not streaming channels. And so what we've seen is a shift of customers going and trying to replicate a channel in the cloud. And that means essentially using something like Media Connect to do contribution into an EC2 instance that's hosting a playout solution. And so that will have, for example, a heavy graphics EC2 instance that can run the visualization and the graphic overlay engine. That will then output into something like Media Live that will create the multi-bitrate HLS stream, which will then go into Media Package to create the packaged endpoints such as CMAF, HLS dash, which will then go into something like MediaTailor. And MediaTailor can do SSAI, and then CDN, like CloudFront, is used for consumer distribution. And this architecture is very common and is totally valid. But what got me thinking is there a way to... Yeah, it's complicated. Is there a way to do this perhaps even more simply, right? And so what we thought of is, can we take existing HLS VOD, Dash VOD, and simply reassemble it into a linear stream based on some scheduling decisions that you can create through the web console or via API. And so I basically got started and tried my hand at this and built a very rudimentary solution on Lambda, but it proved that the core concept could work, and it could work at scale, because we eventually had our very first real-life customer using it, and they were using the rudimentary version that I built called Relinear, and basically they were able to stand up and tear down channels incredibly quickly. So they were able to create a channel purely as a pop-up channel that featured, say, the last season of a TV show to promote the next season, or a Friday night watch party pop-up channel that is promoted on social media or TikTok or something like that to try and get people onto the platform to all watch together. Or they could create very targeted channels based on a show or a genre or a season or even a target demographic. So they could, in theory, create hundreds upon hundreds of channels with very little incremental cost above each channel. Through that process, we learnt quite a lot. So one of the big things we sort of learnt here was the power of efficiency. So when we are delivering video through a live encoder, the live encoder obviously has to encode the video in real time because it's getting a bit stream in and has to send a bit stream out. But when we're using channel assembly to simply stitch together playlists, the encoding has already been done. So it really pays dividends to over-index on the compression ratio you get on the videos that channel assembly is representing as a live stream. And just as an example here, a lot of people would look at HEVC cost and think, well, if it's going to cost me 10 times more to encode in HEVC, but it only gives me 50% bitrate saving, that might not be worth it. But it is worth it when you factor in that you need to distribute that 50% bitrate saving to every single consumer behind the CDN. And so that pays dividends over and over and over again, whereas the cost to encode is only incurred one time.
So that's interesting, Phil. Is that a trend you see from customers using HEVC over H.264 for live content?
Yeah, it's a good question. I mean, traditionally, the costs to do HEVC live encoding have been quite prohibitive, but that's starting to change. We do see some live appliances do live encoding in HEVC now as well. But in the channel assembly world, because you are reusing an existing VOD encode, you get whatever you've encoded for free. So a lot of customers already have VOD encodes with HEVC ladders in them, and because of that they can simply reuse it, and they may as well because it's sitting there waiting to be used. And then once they include that, all they get is the bitrate saving at the CDN level, so they can give the users that have HEVC compatibility the same quality experience but at 50% less bits. So we see roughly half the customers that have started using channel assembly using HEVC tiers. Yeah.
Okay. Interesting.
And then I suppose just one last point that I think is quite interesting with channel assembly streams is the ability to include segments from the future. So because channel assembly understands this schedule ahead of time, it can simply move the DVR window of the playlist to include future segments. And then the player will download those segments from the future, and you can extend out that forward buffer without changing the latency. So the latency will be 0, but the forward buffer goes off into the future, and you can have a forward buffer of many minutes, which is similar to, for example, of a VOD style forward buffer. Yeah, on-demand content. So the net result of all of this is that you have a linear stream that has the same video quality as, say, VOD encode from Netflix. It has incredibly low rebuffer events because it is being downloaded so far into the future. Is highly robust because there's no just-in-time encoding happening. It's all just manifest manipulation. It's also very cost effective because of you're not touching any bit streams.
Sure, interesting. So you do get a more stable stream using channel assembly rather than using a live traditional stream where your channels are being created.
There's so much less that can go wrong. Yeah.
So what you're showing, it's really manifest manipulation. And what's the difference between SSAI and what you're showing? It's basically the same.
Yeah, I mean, funnily enough, actually, I've got a slide on this exact topic. So yes, SSAI, server-side ad insertion, takes an existing linear stream or VOD stream, it doesn't actually really matter, and it will essentially insert VOD segments into that playlist, right? And those VOD segments are the ad creative, are the commercial breaks that have been signaled by the ad decision server. And so where channel assembly is different is it takes that concept one step further and allows you to stitch together those VOD segments, which can be your own VOD catalog, and create a net new channel without a manifest to manipulate, if that makes sense. So it's not so much manipulating an existing playlist, it's synthesizing or generating an entirely new playlist based on VOD playlists, if that makes sense. And I can show a small demo towards the end, and hopefully it'll make a lot more sense then as well.
And maybe before moving to the demo, can you also add SCTI markers? If you want, for example, if you want to place ad breaks, can you place SCTI markers?
Yeah, so that is absolutely one of the biggest requirements, because most of our customers that are creating channel assembly streams are doing so in order to insert ad breaks and therefore monetize these channels. And so the ability to insert ad breaks mid-roll is also very, very important, because if you have a VOD asset that doesn't have any ad markers in there, channel assembly will still let you, via an API or via the UI, simply define at what offset an ad break should occur. And then you can insert the ad break slate, and then the slate will be replaced by the downstream server-side ad insertion. So yeah, that feature is really, really important and quite widely used. I can talk a little bit about the architecture for channel assembly. So as you can imagine, because it's so similar to SSAI, it sits within the MediaTailor family. And so MediaTailor has been used for many, many large-scale live events. We've had a lot of experience in dealing with different types of playlists, so all of the crazy edge cases you can imagine with different types of playlists and how they're assembled. Yeah, we've seen it all, and so we've used all of that learning in order to create the channel assembly origin. Another really important thing is performance, right? So being able to process these playlists very effectively is something that we've built, through a lot of hard yards of doing that with MediaTailor SSAI. So once you log into the AWS console or use the API via the CDK or the SDKs, you can go ahead and configure channel assembly. And so channel assembly will work with either existing AWS Elemeental services, such as Media Package, Media Convert, and also CloudFront for CDN, but you don't have to use those services. So you can use your own third-party third-party origin and third-party CDN. You can use an on-prem origin. None of that matters, because we want to encourage reusing existing assets wherever they may lie. So we have some customers that are using their own origin on AWS behind Elastic Load Balancer, and that again is totally valid. It just depends on the customer's architecture, how they set that up.
So you're like MPEG Dash, you're agnostic,
Yes.
CDN agnostic.
We try to be as agnostic as possible, and it's all in the effort of reuse. So if you've already spent the time, effort, money in optimizing your VOD catalog, why not reuse that and create a linear stream from it, and therefore double your effectiveness of that VOD library. Should we talk through the demo slides now?
Yeah, for sure.
So this is a small set of screen caps from the AWS console. And if you were to log into the AWS console and go to MediaTailor, you would see the channel assembly heading on the side. So I'm just going to walk through some of the key resources that you would create. The first one is the source location. So the source location is more or less the origin of channel assembly, but because channel assembly itself is an origin, we didn't call it origin because it's sort of a circular reference and a little bit hard to use that term when it's used in so many other places. So what that actually really should be seen as is what's the upstream content repository that hosts your VOD playlists and media segments. So that can be a just-in-time packager, that can be an S3 bucket, that can be your own web server. It all depends where they are hosted currently. What's more is that you can define a segment delivery server as well. So if you have an S3 bucket that has the HLS, has some security requirements. That's a great point. So if you have security requirements about going direct to origin, you can include signatures for S3 access and also signatures for media package that's coming soon. Then you will then be able to authorize channel assembly to go direct to the origin or direct to the content repository. But then on the resulting playlist that channel assembly gives to the users, there's a CDN prefix. And so consumers will download those segments via the CDN prefix that you specify here.
So in the case of S3, it will be CloudFront.
Yes, so CloudFront or any CDN for that matter. It's completely up to you what prefix you put there. So you can put whichever CDN works in that case. You can even use the CDN as a repository. So the CDN can be used as the source location for channel assembly to go and get the playlists for the channel assembly process. So let's talk a little bit about adding an individual VOD source. So let's assume I wanted to add this source, which is called Mozart in the Jungle 401. So that's just an episode of a TV show that I want to include in my content sources that are later scheduled for playout. And so here you can see that I'm simply giving it a name. I'm giving it a source group. And what the source group is a way of tagging playlist types that are compatible with one another. And so in this case, I might have a package configuration for HLS, and I might have one for Dash, and I might have one for HLS with fair play encryption. I might have one with only HEVC. However many different, I would say, master.m308s or master MPD playlist files you have, you can create a source group for each one. And then that source group tells channel assembly that these two playlists are compatible with one another. They have the same number of bit rates. Each bit rate corresponds to another bit rate in the other source as well.
Cool. So you can have multiple flavor of each source.
That's exactly right. Yes.
Addressing each devices later on.
Yes. So you said that at this. Yes. Sorry. Go on.
Yeah, quick question regarding the catalog, because clearly what you're doing, you're creating your on-demand catalog to create a live channel. Can you do it manually or automatically program?
So there's a very kind of comprehensive, easy to use API. So you could, in theory, scan your existing VOD library and ingest that into channel assembly with simple API calls. And we have customers that have, inserted a few hundred sources into channel assembly without any problems at all.
Cool.
So let's now assume that we have our source location, which is the server that hosts the content, and we have our individual sources. So it's episode of TV shows, movies, documentaries, whatever the case may be. Now it comes time to create a channel. And as you can imagine, the channel is the output of channel assembly. It's the actual linear stream that's in HLS or Dash or however many package formats you have as source scripts. So here I'm just creating a channel with a name. I've got the playback mode as loop. So that means that basically when it gets to the end of the schedule, it'll just restart. So you can create a channel that runs forever. Here on the output side, I'm corresponding the outputs to the source groups that exist in my sources. So if you remember earlier, I had one called HLS and I had one called Dash, and they correspond here so that I can link them together once and then never think about it again. So I'm always operating on every single source group that exists in my content library. So there's no need to create a separate channel for my HLS flavor of my content or a separate channel for my Dash flavor of my content. It's all within the same channel.
And all your outputs will be synchronized then.
Exactly. They'll be synchronized to the same schedule, and they all cost the same. So it doesn't matter how many flavors you have, the price is the same. You only pay per channel and per hour that channel is running. So it becomes very simple to calculate and understand how much a channel is going to cost you over time. You can also attach a access control policy to a channel. So if you want it to be only accessible via other resources, like, for example, an SSAI platform, then you can set that policy up here as well. But in this case, it's just set to public in this example on screen. Now that we have our channel, we need to create a schedule. And the way you create the schedule is by first creating programs. And so what a program is a temporal slot that exists within the schedule. So you might have a program here, followed by a program here, followed by a program here. It's essentially just like a timeline you would see on like a video editor or something like that. And then within each program, that can reference a source. So you can have program A, reference source 1, program B, reference source 2, so on and so forth. And so in this case, I've created program first, and that is referring to this asset, which is Goliath 201 on this origin here. You'll also notice down the bottom, there's a playback configuration box, and this is how you set the order of the programs. So in this case, I can set program first to happen first, and then I can set program second to be relative append, so it happens after the first program. And then the third one I can make here. And then if I wanted to make a change, I can then insert a program here and everything else gets shifted out. So it's like moving things around in a timeline is how you design the programs.
Cool. And also, Phil, can you get multiple sources? For example, I have a source from a CDN A and a source from another CDN. And can I create from the same channel? Can I use these two different sources?
So at the moment, there's only one source per program. But the reason we've decoupled it is because in the future, we want to look into doing dynamic program replacement. So I'm watching one program and it's, a TV show A, and you're watching the same program, but it's TV show B, depending on some rules somewhere. All right. So the program is the temporal slot, and then the content is filled via the source. So we could have very different sources. And so, for example, the program might be comedy, but the actual source in that comedy slot is different for you and I, depending on how you want to configure that. And so the final part to scheduling are ad breaks. And so here on screen, you can see that you can configure ad breaks by simply defining the offset in milliseconds of where that ad break should occur in the program. So if you set an offset millisecond of 0, that's a pre-pend or a pre-roll to that program. So play the ad, then play the program. But if I put a offset of say 60,000, then it would be a 1 minute insertion. So the program would play for 1 minute, then the ad would insert, play the ad break slate, and whatever the duration of the ad break slate is, that's the ad break duration, and then go back to the content. And that would also extend the length of your schedule because it has to make room for the ad slates as time goes on. Finally, you can also set the output of channel assembly to be the input to MediaTailor SSAI. So all of those ad breaks that we've created will naturally work with SSAI. So if you then take the output channel URL and use it as the content source in channel assembly, then you will basically get the SSAI platform over the top as well. And each ad break is then dynamic per user.
Great. And we can see directly from this link a demo of what you just showed us.
Yeah, so this is just a little sample of a linear stream created with channel assembly, and there'll be ad breaks in there as well, and you can see that it'll just work in any HLS player.
Great. Thanks, Phil, for all of this explanation. I feel it was really useful, very interesting.
No problems. Thank you, Raphael. And the service is obviously fully generally available, so anyone can log into the AWS console and start playing with it. All of the documentation is online, all of the pricing is online, and there is no restrictions in terms of people using it today.
Great. Thanks again. Back to you, Paris Videothèque. Bye. See you soon.
Thanks, everyone. Bye.
Thanks.
Thanks, guys. We're going to take a 1-minute break, and when we get back, we will have Daniel from Bitmovin.
Ladies and gentlemen, I want to introduce for you my new song. Please, I want everybody dancing, dancing, dancing.
Hello everyone, and welcome to my presentation on why time series databases are a bad fit for video analytics time series data. I know it's a long title, and I will hopefully shed some more light on why we chose this. But really, in essence, it's talk about what we learned during the last few years building and scaling a video analytics system here at Bitmovin, and all the things that we thought were true about time series and why they're a great fit for essentially time series data, but that just didn't hold any water when looking at video analytics and the involved parts with it. So getting into it, who am I first? Hi, my name is Daniel. I'm the engineering director for the analytics product here at Bitmovin, located in the currently not so sunny Klagenfurt in Austria. And if you have any questions or feedback or anything, please reach out to me. You can reach me at dhi@bitmovin.com or on Twitter @tgrain. Good. As we already started talking about time series in the title, I thought let's get started with a definition of what a time series actually is. So people that haven't worked with time series before have a little bit of a context. So a time series is actually very simple. It's usually a tuple of a measurement at a specific point in time. So classic examples for time series are temperature, stock price, car speeds, flow rate, CPU usage, all things that you're usually observe at a certain point in time and then store also at a certain point in time. So it would be, for temperature, for example, you would usually have something like, let's measure the temperature every day at 8 o'clock in the morning. And if you have, and put it in some measurement log or something, and then you can plot that time over a certain time frame. So obviously, this, if we do that, we end up with a table of data. So we have the dates and then the temperature. And then very easily, you can use Excel for that, you end up with a graph. And that's what people usually associate with a time series. So you have some measurement that you can then plot over a time axis, and that gives you some indication of trend or information about where things are going. And then it's important to understand what is video analytics and why we're talking about this, because it's essentially still graphs, but it's a little bit different. What we are talking about when we mean video analytics is we are tracking relevant metrics for video service. So our customers are not end users per se, but our customers are OTT providers, ISPs, anyone providing online video, and we measure things for them. So we measure how many people are watching something, what the median startup times are, what bit rates are being consumed on the platform, which devices are being used, where are my customers from, what errors are happening. So we're really trying to provide a full-fledged monitoring system around your video service. And all this comes together and boils down to be called video analytics. And it's a very fluent term, can mean anything really. But for us, it's really about measuring something useful to our customers for them to be able to go and optimize their experience for their customers and really guide them towards insights, basically, and give them the tools and the data to change their service. But in essence, it boils down to what we saw before. It's a graph plotted over a time axis. So you have the time at the bottom, in this case, the last 3 days, I think, and then we have how many people have been playing. And it's going up and down, up and down. So where does this data come from? All of our data originates from customers. So we have something called the collector, and it's either JavaScript, iOS, or Java-based collector that you have in your app or on your website that hooks up to the video element and listens for all the events that are happening and makes sense of what's going on. So we end up with something like a log of each session, what happened in that session. And down there, this is not the actual payload, but it looks something like this. So I have something like a time, when did this event happen, or when did this state transition actually happen? It's not an event per se. Then you have a user ID, which is the session ID, not really user ID. And then, okay, 250 milliseconds of startup time. This span is 250 milliseconds long, or 249 in our case. There was no play. This user didn't play, didn't pause, had no bitrate in this startup sample. And then there's the next sample in the log, which happens 5 seconds later. It's 5 seconds long, means 5 seconds were played at 1 megabit, and so on. 30 seconds at 1 megabit, and then there was a pause. So 2 minutes of play duration, 2 minutes of pause, no bitrate. This is the data we get sent from our customers. So anytime from users, so really users going to the website. So every time the collector has any state transition happening, they will send out back a beacon, one of these rows here, to our system. And a very naive way to build a video analytics system would be to just take all of this stuff, throw it into a huge database, and it's going to be fine. How hard can it be? Databases are super efficient. There must be some big NoSQL database out there or whatever that can handle the amount of load we are doing. So that's how this whole thing began years and years ago. And yeah, how much data could that even be? I mean, well, now we know. We currently average around 80 beacons per session. So that means each viewer, each stream that's being played generates around 80 of these payloads that hit our backend. Each of these beacons can have something around 100 plus fields. And yeah, if we then do the math, 1 million plays per day would mean 80 million rows per day. And not so bad, 80 million is something you can fit in a database. But then you go to data retention, and data retention really gets you here. It's for 90 days, it's already 7,200 million rows, so 7.2 billion. And for 365 days, it's 29 billion 200 million rows. I had to check this up on Wolfram Alpha, as this number is just so mind-boggling, has so many zeros. And this here you see where it really breaks down with this storage model. And the thing is also, this is only for 1 million plays per day. 1 million plays sounds like a lot, but it's actually not. I was curious, so I checked, and apparently this online video thing is a huge market. Didn't know that. No, obviously we knew, but I checked the numbers for YouTube, and YouTube has 2 billion logged in users per day, and these people are watching more than 1 billion hours of video per day, and the average visitor watches around 9 videos per day. So that would be something like 18 billion videos per day. If we come back to our calculation here, for the 1 million, we would have to calculate this by 1,800 or something. So it really falls down completely. Nothing would ever be able to store this amount of data with this model, with this very naive model which we started out in the beginning. Yeah, so lots of data means lots of issues. Anyone that tried to store a lot of data will find out that disks are really expensive, even though we are in an age where you can get a terabyte SSD for your laptop for really not a lot of money compared to 10 years ago. SSD space on servers is expensive. AWS will charge you quite a lot of money for that, and so will Google and Azure. And then there's also this issue that lots of data also means that you have to take into account lots of data. So if you have to, to calculate one metric, you have to scan through an index with 2 billion data points, you still have to read 2 billion data points. It might only be 2 billion data points of like a few bytes per data point, but still it's a few billion of those. And the query will take a lot of time, and it will end up timing out, or your users being frustrated and all that stuff. And then also queries use a lot of compute. So at a certain point in time and scale, you will have to distribute the load, and you will have to use some sort of distributed database system that can handle this amount of load. And first of all, these don't come cheap. They are not easy to operate, and they use a lot of compute to do all of these things. So lots and lots of data, lots of issues. And so in the end, you have to ask yourself, we're scanning and storing 29 billion rows just for displaying this graph? Well, we thought that's silly, so time series to the rescue. Someone said time series are super efficient, let's use them. Well, why? First of all, the one key motivation for us was also to decouple viewers from storage requirements. Obviously, if everything you store, every time you store something, for every viewer you start storing some per viewer data, that means that very, very big accounts scale linearly with the amount of viewers. So 100 million viewers will require 100 million times this amount of storage per viewer. And that means that for very, very big accounts, you end up storing a lot of data, and going through a lot of data, computation is expensive, all this stuff. So if you go with the time series, you're not storing the viewers anymore, but you're storing the data point at a certain point in time. So if I just store, okay, yesterday at 10 p.m. we had 17 people on the platform, I'm storing 17 and 10 p.m. That's 2 data points. And it really doesn't matter if it's 17, which would be the case for my website, which has, 17 is even a lot for my website, or it would be for ESPN, where it might have been 200 million people, I don't know. So it really doesn't matter how many people watched, it only matters how many data points we're storing, and we're storing data points that are rooted in reality, in time, so per minute or per second or per hour or whatever. So that becomes incredibly simple. And storage cost also becomes extremely predictable, because it's really the retention time times the granularity times the series. So if you store minute interval data for a week, that's times the amount of series you're storing, the amount of metrics. That's a number you can calculate, and that you can very easily price. And then also lookups are insanely fast and bounded. So I was shocked to find this out, but it's only 525,000 minutes in a year. That's it's 500,000 minutes, but it's only 500,000. That's something that you can easily store in a lot of different types of storage and retrieve without any issues. So essentially, lookups become of a linear complexity. So it really only depends on the retention time, how fast you can look stuff up. And that was the basic promise that we hope to gain from using time series. So we thought, let's go to work, let's do it. It's gonna solve all of our issues. That's the way to go. And then we had to find out that's not how you do it. There is no free lunch, and especially with data, and especially with stuff like video analytics, where there's a lot of different conflicting things going on, you just can't switch the database type and hope to gain everything from it. there's really reality kicks in. You find out, okay, this doesn't work, that won't work, and this is. And what I want to take you on here is a little bit of a story of what we tried and what didn't work. Because if you think about it, it's not really one time series. It would be nice, but it's not. Like we said earlier, we have this different question that customers ask, like, what platform are my viewers on and stuff like that. If you just look at, that's not one time series anymore. It's multiples. So you have each breakdown that we have in our dashboard gives you one time series. So here we see Chrome, Firefox, Safari, Chrome Mobile, and Edge. All of these graphs are individual time series that have to be stored. So just this very simple breakdown that only shows the top 5 browsers on our demo on a demo page already require 5 different time series. And then you have to ask yourself, what do customers really need for this tool to be useful to them? And customers they ask stuff like very innocent questions like, what browsers are being used? What devices are being used? Where do my customers come from? Some customers have core markets like the US and don't care about the rest, but others are global players. Also in Europe, a lot of customers are based in Germany, for example, and are focused on the DACH region, so Germany, Austria, and Switzerland, the German-speaking part of Europe. You want to be able to query data by where they're coming from and where it's coming from. And then maybe in Germany, certain devices are being used that are not being sold in Austria, for example, and you want to know these things. And if you run the cardinalities for these things, well, let's estimate that browsers, let's say there are 20 to 30 browsers that are actually useful, that are actually relevant. Then we have, let's say, around 100 different devices, so iPhones, iPads, different types of them, Android devices, TVs, all that stuff. So 100 is not a lot, especially if you have it's a very long tail in device usage, obviously. And then there are 195 countries in the world, or 193, depending on where you put the Holy See. But all these 3 questions already give you a lot more time series. So you end up with 30 time series just for the browser, 100 for the devices, and then 195 for the countries. So it's not just one. And then customers tend to combine these questions. So you want to be able to know which browsers are being used on Android in Germany. And this doesn't work anymore with just time series. It still works with time series, but you have to deconstruct the time series into time series that represent the specific tuple. So you have to do Chrome, Android, Germany, Chrome, Android, Austria, Chrome, Android, Switzerland. And if you do this, you end up with a Cartesian product. So it's it's 30 times 100 times 195. So just this very simple triplet of breakdowns, browser, Android, and browser platform and country, gives you 600,000 time series just for this very, very simple thing. And well, time series, the cool thing about time series is that they can be very efficiently stored. So 600,000 values would only represent 1.17 megabytes in Prometheus. But that's not the whole story, which we found out. Because obviously you have to store all the strings for your browsers, for these combinations of browser platform and country. But anyways, even if we calculate this with 1.2 megabytes, if you just add the video title to that, you calculate the whole thing, you once again create a Cartesian product, and you end up with 585 million time series. And 1,000 videos in a library, so being able to then filter down what video was watched on which browser, in which country, on what platform. 1,000 videos is not a lot in a library, so especially if you have something like a news site that has a lot of long tail video there, cardinality really explodes. We had customers with millions of videos, literally, and that just breaks pretty much every promise you thought you had towards kept cardinality with your videos. So cardinality will kill you. That's the basic message here. And also cardinality is really, really important for time series. So there's this is screenshots from the InfluxDB hardware sizing guidelines from I think a year ago or something when we checked it last. And you already see here that the unique series, if you have more than 10 million unique series, they already put this in the probably infeasible category. It means that really you're doing something wrong. You need to change your schema. You need to rethink what you're doing, because more than 10 million series is bad for you. And a series in time series, and what they call a series, is really a combination. You might only have one named series like plays, but then all the different labels and tags on them, like browser, platform, these are all then generate series in the end. So you have to compress this down. And they also have this nice graph there. Unfortunately, it doesn't have any scale on this side, but still you see there's an exponential increase in memory. So this is RAM, and RAM is the one thing that we're still pretty limited on, I would say. If you increase the number of series, you're also exponentially increasing the amount of RAM you need. So 10 million series is pretty much the end of where you get. This is already 32 gigabytes of RAM on the server. You wouldn't get to 20 million with the biggest server you can buy. So yeah, there's a hard cap on that. And going back to how many time series do we actually need? Well, we have in our dashboard something like 40 metrics that we present. Then we have 20 plus breakdowns with varying cardinalities. So we allow breakdowns by country, breakdown by device types, device classes, breakdowns by ISPs, which is totally unbounded, basically. Yeah, and also countries, but also custom data values. So customers can put their own tags on things, and these don't have to be, there's not a limit to the upper cardinality of these fields, or not really. So this means that things, especially with the multiplicative nature of these data fields and how they impact cardinalities for time series, things really break down really quickly. So obviously, the first thought you have in this case is let's do top K. Let's aggressively reduce cardinality. We want to use the efficiencies of time series, and no one really cares for more than the top 15 browsers. This is where you want to optimize for. And this then really, like with everything, it becomes a product decision. You're talking to a product manager and you're talking to customers. How much do you really need? And I mean, while experimenting with this, we really only tried to see if it's feasible before we go out and ask customers. But we thought like, okay, let's cap it to 15 browsers. Let's only store the top 30 videos, and let's only store the top 30 countries and the only top 10 most used devices. So doing the math again, 15 times 30 times 30 times 10 leads you to 135 time series, 135,000 time series, which is a lot, but it can be stored and it will not explode any of your databases right away, right? But then you find out that top K is really, really the problem. Top K is hard. And I put some bogus browser data here, so this is totally made up just for this example. But what would the top 3 browsers out of these 5 here really be? We have Chrome. We have Chrome on top. So here you see this blue line. This is Chrome. And obviously, I would say it's easy to see that Chrome is the top browser throughout our dataset. But then we have Safari climbing up here once and having a few good days, and then it's clearly number 3. And then we have Firefox here, pretty stable. And then we have Edge, which started climbing somewhere and then became the second most browser at the end of this whole dataset. If we look at the table, as I said, this is completely random data. I just created this for illustration purposes. We end up seeing that Chrome obviously is the biggest browser in total, but Firefox and Edge really are close together, and Safari is the second most used browser. And what you can already see here is it really depends when you put the end and the start dates, which are the top browsers. Because in each day, different browsers are the top browsers. And if we were to exclude Firefox, it would look like Firefox is really not there, although it's clearly the second most used browser in the first day. It's the third most used browser the second day, and then it declines because Edge comes up. And then it would look like the total really looks weird because you're missing this very important data point in here. So top K is a little bit of a tricky thing. And we played around with having a buffer. So it's really, the problem is with the stuff on the bottom. So if you say you're taking the top 5 browsers, it's really a problem for the top 5, for the 5th one that might fall out or come back in. So we started building in something like a buffer where we always store 8, but we only show you 5. So we have like one that's coming up, where we have a situation like where we have a situation like this. So a smaller browser comes up and overtakes another one. So if the total would overtake the other browser, it falls out basically, but we still have the old data. And that worked to some extent, but it leads to this issue that you're always looking at data over time, and depending on what time you're looking, on what time you're querying, you're looking at different data, and that's super weird. And also, one thing which worked really, really well for browsers, like this buffer and over like storing more than we actually need and stuff like that, that works for slowly moving values and stuff that's always there, like browsers. Chrome, Firefox, Edge, Safari, Internet Explorer is hopefully gone now. But these are always there. These browsers don't change so much. So it's really the distribution that changes. But where this falls totally down, and which is a specific thing about video, is video does not have this characteristic that everything is always there, especially in live video. So an example, let's say you take some daily news show, and I Googled this. There's like news shows in the US that have 2 million viewers per day. And if you run the numbers, this news show runs 365 days a year. It's 730 million views per year. So clearly this will be one of the top videos on your platform if you're live broadcasting television. And you track all of it with the analytics tool. And then you have the Super Bowl, which is probably the biggest televised event every year. And the Super Bowl lasts for a few hours. It attracts 91.6 million viewers, I think, last year. So 91.6 million versus 730 million. Obviously, the daily news show wins. If you have to choose the top 15 videos on your platform, the Super Bowl will never make it. There will be some very low volume programming that is weekly or daily or whatever that will always in total be bigger than the Super Bowl was. And especially for one-time things like a presidential address, inauguration or something, all of these things that only happen once and have a very high viewership, they will never come into play with the top K algorithm, because the top K algorithm always will reduce them out against stuff that has higher volume, but with regards to the time. So with any regular programming, super events will never end up in your top K. And if you take the top K for each day, the graphs end up having a lot of gaps. So we could say, let's always take the first 3 browsers in the day. Well, once these change, you will have a graph, you will have a series just show up that wasn't there before. So it will look like 0, 0, 0, and then it's there. But maybe there's a series that alternates. Like you have let's say Edge and Safari in our example from before. They really only change places every 2 or 3 days because they're really close together. It would look like the one is 0 and then it is there and then it's 0 again, while in reality there were data in between and they were just not there. And so also the totals over these will never be correct because you have the zeros. And yeah, the next problem is that they still require the same amount of time series. Just because there is no value there, it still means that the time series itself is there. It just didn't contain that many values as the other one. So we still end up with a ridiculous amount of time series. And this is where everything breaks down. So time series are dead, right? Rest in peace. Nothing to see here. Thank you all for coming. No, obviously joking. There are some other properties of video analytics data that we can exploit and where time series then still are useful. Because video analytics is still time-based. We still look at data that's essentially a graph over time. And still all the events that happen are time-based. And one cool thing about time-based workloads is that they are append-only. Unless you have invented a time machine, which would be probably paradoxical and stuff, but also give something really cool. We are never inserting data. We're never looking at the past. So data that's coming in is always coming in real time, and we can't go back. So once data is written, it's immutable. And time series can be super, super useful for caching and can also alleviate a lot of things and issues with our current model. So what we essentially did when we started thinking about this time series thing, we also always knew that we will have a certain degree of live data and then the time series. So we came up with a model, with a system called the splitter. And this is now an integral part of the system that takes time and splits it into smaller parts, takes a query and splits it along its time axis into smaller parts. And this allows us some flexibility in what we're querying, and we can even blend multiple data sources. So as you can see here, what we essentially do is we take the normal graph and then we break it up into multiple chunks. And each of these chunks can be scheduled to different parts of the system. So we can have multiple databases handling different parts of the your data. So we can essentially do sharding first of all in the main database we have, but we can also blend data with things like a time series database where we have it, and it's no longer a binary decision. So we don't have to solve all of our issues with a time series, and we no longer have to solve all of our issues with a regular database or something like that looks like a regular database, I would say. But we can blend these two. And just having the splitter gives us the huge flexibility. And one other really cool thing is that was enabled by the splitter is that it also reduced the loading times a lot by doing parallelism that wasn't there before, which is a little bit weird, but still. And the other cool thing is it also give us the ability to do visual indication to the user. Because if you're going through 1 billion data points, that will take a lot of time, or not a lot, but it will still take a few seconds or 30, 40 seconds, something like that. But customers understand that. If you're looking at the graph of the last 6 months on a very, very high traffic site, you expect that to be not slow, but you expect it to take some time. And this, as long as there's visual feedback, you're okay with that. And by having this split and being able to calculate parts of our graph while the user is waiting and feeding him the results in increments, we end up giving a much better waiting experience. So having essentially a loading indicator by showing the graph, how the graph builds itself to be the final one. But also users tend to be more patient and forgiving for slow performance, essentially. And then we can then use something like cache time series. So everything that we query and the individual splitter parts are being cached and being merged with the real data that we have on the one end, but also it's we can also pre-calculate a lot of things, a lot of time series. Like one thing we can do is there's one graph that everyone sees. That's when you come to the dashboard the very first time. There's one graph that we always show. This graph never contains any filters. It never contains any breakdowns. So it's essentially a very static graph. And just by pre-computing that one graph, we can already make the experience instant for any user coming to the platform by storing this in a time series. So coming to the learnings here, yeah, time series have a place, but you just can't solve an issue that requires real queries and real like high granularity indices by using time series. Time series are an aggregate. Time series are a condensed version of that can be used to improve performance, that can be used to cache things, that can be used for certain specific use cases, like very long-term storage, where customers, we're also thinking about giving customers the ability to specify specific graphs and metrics, very like 1 or 2, that they can then store for very, very long amounts of time, because then it's just this one time series, but they also don't have any ability to filter that or something. And high granularity is a huge feature that we don't want to miss. This is really why you want to have a video analytics system and why you want to have the data we collect. So condensing that down and trying to fit that in a time series that's always a lossy operation really provides no benefit. So really, there is no free lunch. There are only different trade-offs. You have to take different databases for different types of workloads, and you have to blend and match them. And one of the best decisions we ever made there was to create this technology, this splitter, that's now more of a query coordinator that can blend different types of databases and different types of storage methods and models together to provide this one data, this one time series that ends up on being rendered to the browser. So, and you have to really embrace time-based data and the trade-off that this gives you, the trade-off flexibility this gives you. So we can say the last 2 weeks we can query from this part, and the other stuff before that comes from another part of the database or from another schema, and that's really, really useful. Yeah, and really the next thing is analytic systems can't be solved by only one database model. That's the hard thing. If you go with a more traditional database model, it will limit your ability to do very long-term retention. And you really have to play to a database's strengths, to the data model strength. It really doesn't matter which database you use. If you're using Prometheus or Timescale or whatever, it really doesn't matter. Every database will have its strengths and weaknesses, and you really just have to be very aware of the strengths and weaknesses and use each database for what it's good at, and try to minimize or try to not fit square pegs into round holes in the end. Yeah, so that was a little bit of a story about what we learned when trying to move to time series databases here at Bitmovin. I hope this was interesting to you. Thank you very much, and see you next time.